Alright, so for this video, I'm just going to show you how to do this particular elastic collision. I just picked a couple of random masses here from the simulations. The red one on the bottom left is 3 kilograms. It's moving to the right at a positive 9 meters per second, as indicated here. And then the bottom right, blue, is just 1 kilogram, and that is moving to the right at 1 meters per second. So I've chosen a scenario here where the blue one is going to kind of move really slow, and then the red one is moving faster in the same direction, so I'll actually catch up and bump it. Okay, so I'm just going to hit play real quick here so you can kind of get the scenario. I'm going to hit pause. We'll do the video and then confirm that the answer comes out. And if my dog is barking, I do apologize. She is apparently being ferocious. Okay, all right. I'm going to start, and then boom. Okay, it's going to collide, and then it's going to, go through this elastic collisions. All right, so once again, mass here in red is 3, mass here in blue is 1, moving to the right at 9, moving to the right at 1. We'll do the calculation, and then I'll hit play again, and then, you can kind of see how to attack these types of problems, okay? All right, let's go ahead and get this presentation going. So here, it says a 3 kilogram moving to the right elastically, key term there being elastic. That will imply they will bounce back, and conservation of energy is also conserved in addition to conservation of linear momentum. Part A wants us to find the velocity of each after the collision, and then part B wants us to find the magnitude of the average net force exerted on each cart during contact. So of course they hit, and what is that force during that particular contact time. Okay, let's go do part A. Part A is a little longer. So to do part A, I'm just going to identify M1 being the red one, M2 being the blue one. And then I'm just going to make this statement. M1 is 3 times M2. M1 is 3 kilogram. M2 is only 1 kilogram. So M1 is just 3 times as massive because 3 times 1 is 3. All right. So keep that in mind as I do my work here. So I'm going to start with conservation of the momentum. Why? Because the system has to be conserved. So here initially I have 2 terms on the left. I also have 2 terms on the right because this is an elastic collision and they have different masses. So I'm going to go ahead and do this. P1I plus P2I equals P1F plus P2F. I'm going to break it up though into MV, and then so it'd be M1V1I plus M2V2I equals M1V1F plus M2V2F. But you notice here in my work, I highlighted M1 because earlier I said that M1 is 3 times M2. You don't have to use this particular strategy because all the values are given to you. You can just simply multiply, but I like to do this because I like to cancel things out. All right, so here I can substitute out M1 for 3M2, and then I can do the same here on the right side. And you notice here, once you do that, all the M2s will cancel out. So it cleans it up a little bit. So here I just have 3 times V1. V1 being a positive 9, and then V2I is now just by itself because I've already canceled M out. That's just 1 because the scenario I just chose the initial velocity V1. And then on the right side, it may just be 3 times V1F, but I don't know what V1F is. That's kind of the whole point of A. It asks us to find the velocity of each of the cart after the collision, so we don't know the velocities. All right. And then here on the right side, the very last term here is just V2F, just gets carried down. I'm going to simplify the left side. 3 times 9 is 27. 27 plus 1 is just 28. So here I have the statement now I have with 2 unknowns. V2F is already by itself, so I'm going to go ahead and get that by itself. You don't have to. You can get V1F by itself, but I mean, I would not. Why do that when you have V2F already by itself? So I'm just going to move this 3V1F to the left side, which makes it negative. So it'll be 28 minus 3V1F, which is equal to V2F. Well, as you can see here, you have a statement with 2 unknowns, so you're kind of stuck. So let's go ahead and set up conservation of kinetic energy. I can do that because it says elastically. So one of the conditions for elastic collision is that the KE of the system has to be conserved. So here, I'm just going to cancel the 1/2 everywhere because I know it cancels out just based on experience. So if you want to, write the 1/2s out and then cancel for yourself. You need to practice. So here, initially you have 2 objects moving. So on the left side, you have 2 terms. On the right side, you also have 2 terms. Here, I'm going to do the same thing I did on the left side. I'm just going to get rid of M1 and replace that in terms of M2. So instead of M1, I'm just going to write 3M2. Hopefully have good habits. Make sure you use parentheses so this way your work looks nice and clean. I notice that low parentheses, they're small, but that should be big. Pardon that. And then so M2 is going to cancel out on every term here because it appears on every term. So on the left side, all I have is 3 V1I squared, V1 being 9. I'm going to square that. And then The second term on the left side here is just v2i. I made v2i being 1. We're going to square 1, which is just 1. And then on the left side, the only thing left is the 3 I carried down. v1f squared we don't know. v2f squared we don't know. So on the left side, the equal sign is just a bunch of numbers. So let's go ahead and combine that. So if you multiply everything here, that'll give you that. And then clean it up a little bit. You get 244 equals to 3v1f squared plus v2f squared. As you can see here, on the left side, I have v2f by itself already. On this side, I have v2f squared almost by itself. So I'm going to go ahead and get it by itself simply by moving the 3v1f squared to the left side. So that becomes a negative value now. So it'll be 244 minus 3v1f squared equals v2f squared. But now I have v2f without the square, and then I have v2f with the square. So I think the easiest way to do is just FOIL this term on the left side. So I'm just going to square both left and right. So it'll become v2f squared, but the left side I'm going to square it, so which means you have to write this term out twice. So here I'm just going to FOIL, so it'll be 28 minus 3v1f times itself, because that's what squaring is. And if you do FOIL correctly, you should get 784 minus 168 v1f plus 9 v1f squared. So if you need to practice how to FOIL, please pause here and just FOIL. Make sure you get the same thing that I did. Now that we have v2f squared and then v2f squared, we're going to set both these left statements equal to each other. So here I'm just going to bring my work up. So on the left side here I have 784 minus 168 v1f plus 9 v1f squared, which is right here where I'm circling at the top right of my screen now. And then I also have v2f squared from kinetic energy, which is 244 minus 3 v1f squared. And that's, I want to set those two statements equal because they both equal to vf2 squared. Okay. All right. So let's go ahead and combine like terms and all that good junk. So here's 244. I want to move it to the left side, which will make a negative. So 784 minus 244 will give you 540. The v1f term is by itself. I don't see anything on the right side to combine it with, so I'm just going to carry that down. On the right side here, I see a 9 v1f squared. On the right side of the equal sign, I see a negative 3 v1f squared. So those are like terms. So I'm going to move this negative 3 v1f squared to the left side, which makes it positive. So 3 plus 9 is 12. So it'd be 12 v1f squared. But as you can see here, now you have a quadratic function. So I'm going to identify my a, b, and c. My a being the term with the highest exponent. So this is v1f squared. That would be a positive 12 because the sign in front of it is 12. And my b is actually going to be negative 168. It's negative because the sign in front of the 168 is a negative value. So make sure you pay attention to those details. Excuse me. And then my c here is 540. And then at this point, I'm going to exit my screen. And just to show you, if you have a calculator or if you have a quadratic solver, you can do that. All right, so here's my quadratic. I think the first term, I actually don't remember. What was it? 12, negative 168, and 5. Okay, so it'd be 12, negative 168, and 540. And I'm going to hit calculate. And then my answer here, as you can see, it's 9 and 5. Okay, so I'm going to go back to my presentation here. Okay. Okay. All right. So if you do that correctly, you get v1f as two values. It gave us a positive 9 and a positive 5. But using common sense, you cannot pick positive 9 because it was initially moving already at 9 to the right, which means after collision, it would have to be the other velocity. So here the answer for v1f would be a positive 5 meters per second because it asks for velocity. So I include the positive sign for you. But once you know v1f, watch this right here. I'm going to pull that term right there. Why? Because now I can find v2f. I already have an expression for v2f by itself. So I'm just going to take 28 minus 3 v1f. I just found as positive 5. So I'm just going to substitute in 5. So it'll be 28 minus 15. So v2f is simply going to be 13 meters per second. But it says velocity, so I put the positive sign in there for you as well. If it asks for speed, leave the directions out. Okay. So all right, that's it. Now, part B asks you if the collision lasts for 0.1 of a second, right? Calculate the magnitude of the average net force acting on each car. Well, when they collide, they exert an equal but opposite force on each other. All right, so let's go ahead and find part B. To do part B, I'm just going to go with the mass on the left side. You don't have to. I'm actually going to show you how to do the mass on the right side later on, M2 if you want. Okay, all right. So here's method one. To find the magnitude of the average net force, you can simply just use impulse, the change in momentum on M1. So you notice here's this delta P mass 1 is equal to the average force times time, because by definition, the change in momentum is simply force times time. Therefore, I'm just going to break it up. Delta P is just PF minus PI, and then the right side stays the same. But here, P1F is just M1V1F. P1I is just M1V1I. I know everything already, so I'm just going to go ahead and find F average by dividing both sides by delta T. So here I'm just going to plug and check. M1 is 3 kilograms. V1F we calculated already in part A is 5, and it's a positive 5. Minus, because the function itself is a minus, because it's taking the difference. M1 is 3, and then V1I initial is a positive 9 as well, because I chose it to go to the right. So if you clean that up, and then time here is given to us as 0.1, you'll get a magnitude of, you'll get an actual value of negative 120 newtons, okay? However, the statement here asks for magnitude, so I'm going to go ahead and get rid of that negative sign because that's the direction. And so the answer would simply be 120, okay? Or 120 newtons. Now, method two. If you want, you can use method two. You can just apply sigma F equals ma, Newton's second law, okay? Well, to find net force, we need m and we need a. We know a is to change in velocity over change in time. Well, here we pretty much have everything. Here, mass is 3. Vf is a positive 5 minus Vi, but Vi being a positive 9. So T is given as 0.1. So here, if you do correctly, it'd be 5 minus 9, which is negative 4. And then negative 4 times 3 would be negative 12. And then negative 12 divided by 0.1 will give you the same thing. Or you can just do this in parentheses. You can do 5 minus 9 be negative 4 divided by 0.1, which would be negative 40. However you want to do it, you'll still get the same answer, okay? So the answer here, as you can see, it still comes out negative 120 newtons. But once again, the answer would just be 120 because I asked for magnitude. Now, if you wanted to, you can actually use M2, the blue car, as a reference point. So if you do that, just be consistent. So here, I would say the average force then is the change in momentum. I just carry this function down here. Watch what I'm circling, right? I don't want to set all this stuff again. To find average force, I can just do change in momentum over change in time. So it'd be M2V2F minus M2V2I. Make sure you write the final before you write the initial. All right, other than that, you plug in values. M2 is 1. V2F, we calculated is 13 from part A. Minus M1 is 1, and then V2I I chose in the animation as 1, and then that would be divided by 0.1. So if you do that, therefore you'll get a positive value. But keep in mind, depending on your perspective, your forces are opposite in magnitude, but they're equal in magnitude but opposite in directions. Okay, so as you can see, in one perspective you get a negative 120, and the other perspective you get a positive 120. Okay. Other than that, I'm just going to exit the screen and then hopefully show you that the values we got from this animation. If I can just hit reset and then hit start and then let you watch this. Okay, as you can see, our values were 5 and 13. And once you find these velocities, everything else is kind of super easy to do. All right, stay nerdy, don't be whack.